Good afternoon, all. I welcome you all to the fourth tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harina Chakrapani and Professor Niraja Dashaputre from ISER Pune. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay, and till now we have already conducted three tutorials of this course. So, moving ahead to the fourth tutorial, where we are going to try to solve a few questions on the topics derivatives of carboxylic acids, and along with that, we will solve questions on the topic alcohols, ethers, and epoxides. Okay. I hope my slides are visible to you and my voice is audible. So it's already about 3:10. So let us start with today's tutorial. Okay, so here is the first question of today's tutorial. What is the IUPAC name of the organic compound found in the following chemical reaction? Here you are given a ketone acetone, and we are treating it with Grignard reagent, and along with that we are at last doing workup of the reaction with acidic water medium. Okay, so you are asked which of these four alcohols will be formed in this course of the reaction, or none of these options will be formed in the reaction. So to figure out the IUPAC name of the product formed, let us try to break this reaction down step by step with its mechanism. Okay, so what happens when we add Grignard agent to a carbonyl compound? Here is the given substrate, which is acetone, and we have already discussed the reactions of carbonyl compounds. So, in the Grignard reagent, we have the ethyl anion part and this magnesium bromide cationic part. Okay, so what happens? The anionic part will undergo nucleophilic addition at this electrophilic carbon center. Okay, so this minus charge, look at the arrow pushing here, the minus charge will attack at this carbon and push the electron pair shared between the carbon and oxygen of the carbonyl group towards the delta negative oxygen. Okay, so after the attack, this ethyl anion will get attached at this carbon atom like here we have shown, and because of the push of the electron pair towards the oxygen, oxygen will now attain a negative charge, and that negative charge will be stabilized by the counter cation present in the medium, which is this magnesium bromide. So you will get this kind of an intermediate compound in the course of the Grignard reaction. After that, in the second step, we have added acidic water for workup. So in the workup, what happens? This counter cation gets hydrolyzed, and in turn, you get this alcohol as the final product. Okay, this oxyanion gets protonated, and this alcohol you get as the final product. So this is the reaction pathway that is followed by the given substrate in the reaction condition of the question. Okay, so like this you are getting an alcohol as the final product. And what is the IUPAC name of this product? It is 2 methyl 2 methyl butane 1 all, butane 2 all. Okay, you have to count the longest chain. So you get in the second position, if we are considering this longest chain, in the second position you get a methyl, and you get the newly formed hydroxyl functional group in the second carbon. So it will be 2 methyl butane 2 all. Thus you have the option 1 as the correct answer. Okay, and remember this Grignard reaction always gives a very good yield for these nucleophilic addition reactions of carbonyl compounds. Okay, these when we perform these in lab, these usually give yield above 70%. Okay, so it is a well known and very popular method for synthesis of alcohols. So, with having option 1 as the correct answer for this question, let us move to the next question of today's tutorial. Okay, so the next question is the compound A on treatment with sodium gives B, and with PCl5 gives C. B and C react together to give diethyl ether. So, A, B, and C are in the order. You are given four options, and you have to identify all the compounds that are marked as A, B, and C in this question. They are saying suppose A is a compound, this reacts with sodium to give B, and A reacts with PCl5 to give you C. Then if we treat B and C together, we get diethyl ether as the final product. So let us go through the options one by one, and we will try to check which are the compounds that we are talking about in this question as A, B, and C. Okay. So if we talk about question number 1, so suppose as the compound as the option 1 is dictating, it is ethanol. Okay, suppose ethanol is the A here. So what happens? A should give you B upon treatment with sodium. So what happens if we will treat this alcohol with sodium? We should get sodium ethoxide. Okay, so but here in B we are seeing ethane, not sodium ethoxide. So option number 1 cannot be correct answer. We don't even have to move to the C given. Directly by looking at the B given here, we do not get ethane upon treatment of ethanol with sodium. Okay, what happens? Sodium abstracts the proton from the alcohol, and in turn you get sodium ethoxide. Okay, so option 1 we will directly eliminate. Let us move to option 2. So okay, here also we are given ethanol, and if we treat ethanol with sodium, we get this alkyl halide? No, we will not get ethyl chloride. Maybe with PCl5 we can talk about that, but not with sodium. We will not get ethyl chloride upon treatment with sodium. So option 2 also we will directly eliminate at this stage. Now we are left with three more options. Okay, let's go to option 3. We have ethanol again, and upon treatment of ethanol with sodium, we will get sodium ethoxide. Yes, here we are given the correct product B. And now we will look at the product C. They are saying that upon treatment of A with PCl5, we should get C. Yes, if we treat ethanol with PCl5, it gets chlorinated, that is, we get alkyl halide, and PCl5 is widely used for synthesis of alkyl halides. Okay, that is well known. So we can see that option 3 is given all the three compounds correctly. Okay, on treatment of A with sodium, we are getting this product as B, and on treatment of A with PCl5, we are getting this product as C. So yes, option 3 is correct. But we are still left with 2, and since we have already gotten 3 as correct answer, 5 cannot be the answer, okay? Let us move to the only option left. Is it showing correctly? So let us, this ethyl chloride is the compound A, okay? And what happens if we treat this with sodium? This will undergo the Woods reaction, okay? Where if we treat alkyl halide with sodium, we get alkane. So yes, here the compound B is shown correctly in the option 4. Okay, in the option 4, compound B is also shown correctly. But if we move to the compound C, in 4 it is not correctly shown. Okay, alkyl halide doesn't undergo reaction with PCl5 to give you alcohol. So ethanol cannot be the compound C as dictated in option 4. So the only correct option in this question will be option number 3. Okay, and here you can see the very easy reaction mechanism, the pathway with which the reactions occur. Like it says, when alcohol A is reacting with sodium metal, it will give sodium alkoxide, like here you can see, and and after that, in the second step, like for the formation of C product, you react the alcohol with PCl5 to get the ethyl chloride or chloroethane. Okay, and here you can see the byproducts also, you get HCl and POCl3 as the byproducts here. And the overall reaction you can see here, when we combine B and C, they undergo SN2 type substitution, and you finally get the diethyl ether as the major product. Okay, so this is the diethyl ether moiety which you get upon the reaction of B and C. So with this, you get option number 3 as the correct answer. Now moving to the reactions of epoxides. Okay, you are given here styrene oxide. This is the styrene oxide molecule, and we are treating it with sodium azide. In sodium azide, when you add it to epoxide, you can treat it as sodium plus an azide anion, where azide anion will undergo reaction with the epoxide, either following SN1 or SN2 substitution reaction. That depends on the reaction conditions, okay, which pathway will it follow, SN1 or SN2? That depends on the reaction conditions. If in the question you are given acidic reaction condition, you can expect the reaction to undergo SN2 substitution, okay, because in acidic medium you get the stable carbocation formed through in the mechanism, okay, and those reaction mechanisms have been widely discussed in our previous course, Introductory Organic Chemistry 1. So I hope you remember. And in presence of basic medium, what happens? No stable carbocation formation you get in the reaction, and directly the nucleophile will attack at the epoxide ring from the least sterically hindered side. Okay, I hope that is well understood. So if we look at the question here, Are we given any additional acid substance in the reaction medium, or it is following a normal alkaline medium? So if you are not given any additional acidic reagent in the medium, then you have to follow the steric factor mechanism, which is the SN2 substitution reaction, okay, which is mainly followed in case of alkaline or basic medium reaction. So here no question of stable carbocation arises, and you just have to look at the least sterically hindered side of the epoxide ring, by through which we will open up the three membered ring, okay. So like here you see, in case of styrene oxide you have this side and this side, okay, these two possibilities are here, and you do not have acid, so directly the azide will attack at the epoxide ring from this side, and you will open the epoxide ring by pushing the electron pairs towards the oxygen, okay, and the oxyanion will be neutralized in the course of workup with water medium, so it will get protonated to give you this alcohol, okay. So like you saw, the azide will attack from the least sterically hindered side. But if you were given acidic reagent or addition of acid happened in the reaction medium, what would have happened? You would have gotten the carbocation, the oxonium first, and then the epoxide ring will open up to give you carbocation at this side, and then azide would have attacked it at the carbocation side, okay. That would have been the case if the reaction conditions contained any acidic substance, okay. So these two conditions are followed by epoxides when it comes to epoxide opening reactions. So moving to the next question, here you are simply given this piperidine moiety, and we are treating it with this substituted epoxide, okay. Both these sides of the epoxide are this time substituted, but one side is di-substituted and the other side is mono-substituted with ethyl substituent, okay. So what kind of mechanism will it this time follow? I hope you are already guessing it correctly. Yes, you are not given any acidic medium here, so like we saw in the previous question, this nitrogen atom will undergo attack from the least sterically hindered side, okay, and after it donates its electron pair to this side, the oxyanion will form, and the oxyanion will get proton from the positively charged nitrogen, okay, because since its valency is already fulfilled, after the donation of its electron pair to open up the ring, it will attain a positive charge, isn't it? Because we are donating, we are attacking from this side, so it is giving up its electrons to open. So it is first attaining a positive charge. But after the oxyanion will take up its proton from here, it will again get neutralized, and you get this hydroxy substituent at this position. Okay, it is also following the same pathway as the previous question we saw, okay. So you get the attack at the least sterically hindered site. Let us move to the next question now, okay. this is also this question is also from you can consider from the topic epoxide and derivatives of acids, okay. So what are they saying? Which of the following equations shows the wrong main product? So what happens, four reactions are given here, and you have to identify which of this reaction is showing its product incorrectly. Let us go one by one for the question. In the first question, what are we given? We are given a secondary amine here, and we are treating with it with alkyl halide. Okay, so this amine will undergo attack with this alkyl halide, and you get a ammonium. Okay, quaternary ammonium center is generated. Okay, this reaction is correctly shown. So what happens if in this alkyl halide the Ci bond you can imagine as delta positive and delta negative because of the electronegativity of iodine. So the delta positive charge which is generated at CH2, that will get attacked by the amine nitrogen atom. Okay, this will donate the electron lone pair to this delta positive carbon, and you can show either that iodide is leaving, or you can show that iodide is the counter anion of the quaternary ammonium center which is generated by the attack. Okay, so that reaction is correctly shown in the option A. Moving to the option B, here you are given an ester. Okay, and we are treating it with piperidine here. So what happens, ester has an electrophilic carbonyl center. So again, the electron rich nitrogen atom will undergo nucleophilic attack at this carbon center, and in turn this OET, which is a very good leaving group, will get eliminated. And when you work up with proton medium, that ethoxide will get protonated to give you ethanol as the byproduct here. Okay, so you have to show the arrow pushing from this nitrogen atom to CO. Okay, and this ethoxide will get eliminated to give you ethanol. This can take up the proton from this nitrogen positive center proton also. Okay, because you have to ultimately neutralize the ammonium center which will be generated after the attack. Okay, so yes, this reaction is also showing you the products correctly, because you are getting the correct products, which will be this amide which will be forming, and the ethanol is the byproduct. So option B is also showing the correct products. Moving to option C. Okay, in option C you are given this sulfide, and you are attacking at this methyl iodide. Okay, this will follow somewhat similar mechanism which we have come across at the option A. Okay, this sulfur is electron rich, so it can donate its electron pairs to the delta positive carbon, and iodide can leave. So you can show the product at this as this salt product, where iodide will be the counter anion of the positively charged sulfur atom. Okay, so option C is also showing the correct product which is following the similar mechanism as option A. Okay, so after that we are left with only one option here, option D. So what is happening here, you can see this ETSNA, which you can imagine as Na positive and S minus sulfide, and this will attack at this epoxide ring given here. And are we given any acid reagent here? No, we are simply given the solvent ethanol. Okay, so you have to imagine it as the basic medium reaction. And no stable carbocation formation question is generated here. So what will happen? This S minus will attack at this epoxide ring from the least statically hindered side. So you can imagine that S minus will be attached here, and this ring will get opened up to give you OH at the consecutive position of this methyl. So the correct product will be CH3, OH, CH2, CH2, CH2S, and ET attached to the S. Okay, so what we got, the alcohol is vicinal with this methyl. Okay, but in the product we can see that alcohol or whatever intermediate you get, O minus Na, is not vicinal with the methyl. Rather, they are showing you the product which you will get at acidic medium. Because in acidic medium, first the ring will open to give you carbocation at this position, and this carbocation will be attacked by ETS minus, isn't it? So the given product is actually the product for acidic reaction condition. Thus, you will not get this product. Rather, you will get the product where OH and methyl will be vicinal to each other. So we have identified the option that is showing the wrong main product. Okay, so option D will be the correct answer here. This is kind of the explanation for the reaction, and it is showing that option D is the correct answer where it is showing the wrong main product. Okay, you will easily be able to identify the wrong products in such questions if you thoroughly understand the mechanisms which the epoxide ring opening follows in case of acidic medium and in case of basic medium. Okay, if you understand the basic mechanisms of these reaction, you will easily identify which product you will get in the reactions and whether this reaction is correct or not. Okay, so with that, let us move ahead with the following questions. So again, in this question you are given four chemical equations. Okay, which of the following equations shows the correct main products? So this time you are given four reactions, and now you have to see which one of these is showing the correct main products. Okay, in the previous one we identified the wrong main product, and this time we will see the correct main products. So here we can see a few reactions where these two will be cleavage of ether reactions, and the third one is given as dehydration reaction, and fourth option is elimination reaction. Okay, so let us move to the questions one by one, move to the options one by one. In option A, what is given? This ether is given here. This ether is given here, and we are treating it with, you can consider it as hydroiodic acid, HI. And in the product, you can see this aryl iodide as the major product, and this ethanol as the alcoholic product formed in the reaction. So, to know whether this reaction is given correct or not, you have to know the mechanism that ether cleavage reactions follow. Okay, what happens? Usually, ether cleavage reactions follow SN2 type of mechanism, but when you have such a substrate where you have allylic or benzylic or tertiary butylic carbocation formation possibility, then in those cases only The ether cleavage reactions follow SN1 mechanism. I will repeat. Usually, ether cleavage reactions follow SN2 substitution, but when you have allylic, benzylic, or tertiary butyl carbocation formation possibility, since in those cases you have the possibility to get a stable carbocation in the reaction, then only in those four, three, four cases only you have the follow. If you have a reaction where the ether cleavage will follow SN1 mechanism. So, in option A, do we have any such possibility that we can get benzylic or allylic or tertiary carbocation formation? No, we do not have any possibility. So, simply this reaction will undergo SN2 substitution. By what? By the I minus nucleophile present in the reaction medium. Okay, so I minus can undergo attack at either this or this carbon, but it will not attack at this position. Okay, because this aryl ring cannot undergo such kind of nucleophilic substitution reaction. Okay, so that is why the I minus will prefer to attack at this sterically preferred position, and in turn you will get the cleavage of this bond. This OC bond will cleave and you get O minus at this oxygen, and that O minus during workup will get protonated and you will get phenol and ethyl iodide as the major product. I hope the mechanism was clear. The I minus will attack at this sterically preferred carbon, and this OC bond cleavage will give you phenol as the major product along with the formation of ethyl iodide. Okay, so are we getting phenol and ethyl iodide in the product? No, it is showing the reverse. Okay, so no such mechanism can be followed in this reaction, and you now know that option A is not showing the correct main products. Okay, so we will eliminate the option A from this list. Okay, and now we have option B where you have a benzylic carbon. And what did I say? If you have the possibility of formation of benzylic carbocation, the reaction will follow SN1 substitution. So how is it possible? First, the oxygen will get protonated. Okay, this oxygen in this acidic reaction condition medium will get protonated to give you oxonium, and then that oxonium will get neutralized by formation of the stable carbocation. You can consider the formation of stable carbocation at this benzylic position, and this bond breaks this time. So after the breakage of this bond, you will get ethanol as the product. I mean, first you get ethoxide, isn't it? And that ethoxide will be immediately protonated in the acidic medium to give you the benzylic carbocation and ethanol as the product. And the newly formed benzylic carbocation attacked will be now attacked by Cl minus nucleophile present in the acidic medium, and in turn you will get this benzyl chloride as the product. Okay, I hope this was clear to you all how you got benzyl chloride and ethanol in this reaction. So, are we given benzyl chloride and ethanol? No, it is again showing you the reverse products. Thus, you know that option B is also incorrect. if you want to know how option A and B we eliminated and how we did this ether cleavage, you can go through these descriptions where it is written as uh, how usually ether cleavage reactions follow SN1 mechanism and in which special cases you get SN2 substitution. Okay, this is the explanation which I have already explained to you. And after eliminating option A and B, we are left with option C and D. In option C, you are given catalytic sulfuric acid under heating condition and you are getting this alkene as the final product. So, in case of acidic dehydration of alcohols, as we have already studied, you get the more substituted alkene, which is called Sadzef product, isn't it? So, first, what happens? This alcohol hydroxide will get protonated in presence of acid, and this after the formation of this oxonium at this oxygen, the water molecule will leave to give you a carbocation here. Okay, after the elimination of this water molecule, you have this carbocation here, and as we are heating it, deprotonation happens from that carbocation formed, and that deprotonation can happen from either this methyl or this CH2. But as we know, in this particular case, you get Sage-F product, which will be in which you will get the most substituted carbon carbon double bond formed. So you get deprotonation from this carbon here, and you get a carbon carbon double bond between the two middle carbon atoms of this substrate, isn't it? So thus after dehydration you will get a formation of CC double bond between these carbon, and in turn you will get this 2 butene as the final product. Okay, and thus after elimination of water, that is dehydration, this 2 butene is formed in this reaction, which is definitely correctly shown in this particular option. Okay, so now you know that option C is showing you the correct option, a correct product formed. Okay, we're still left with option D, and let us analyze option D as well. So in option D, you are given a reaction where you have this quaternary nitrogen center. This quaternary ammonium salt gets generated in this way. Okay, suppose this we have this amine, and when you treat it with alkyl halide, you get a quaternary ammonium cation in this particular fashion, and when you react it with dehydrating condition, uh, not particularly dehydrating condition, elimination reaction conditions, if you treat this quaternary ammonium salt, you get elimination of this ammonium along with deprotonation, and overall you get an alkene as the final product. So always remember, when you are given a quaternary ammonium salt and we are treating it under elimination conditions, the least substituted carbon carbon double bond is preferably formed. Why is it so? In this case, we get Hoffman product. Okay, what happens? At first, this ammonium cation is eliminated. Okay, and you get a carbocation here. No. What happens? You have the formation of quaternary ammonium first here. Okay, so this elimination of one proton from here or here, you have two possibilities. Okay, one proton from here will be eliminated or here will be eliminated. So this elimination of proton and the ammonium will happen in a concerted manner. Okay, you already have this sterically bulky ammonium substituent here. That is why when it comes to deprotonation, the proton abstraction will happen from the sterically least hindered side of the substrate. So you have two possibilities here and here. From these two carbons, you have to deprotonate to get the alkene. Okay, since you have this already sterically bulky substituent, the least sterically hindered side proton will be eliminated, and in turn you get a double bond here. Okay, the CH will be abstracted, the CH bond electron will be pushed towards this bond, and this particular CN bond will break to give you the neutralized amine, and in turn you will get the double bond in this position. Okay, so these two are the two possible products formed in the reaction. This is the Sadzef product where you get the most substituted, and this is the Hoffman product where you get the least substituted. And in this case, where you have a sterically bulky group to be eliminated, you get the Hoffman product as the major product. So in the option given, are we given the Hoffman product? No. For this particular example, after the elimination of this ammonium, you should have gotten a double bond between these two first and second carbon atoms. Okay, but in the product you are given the double bond between the middle two carbon atoms, which is not possible. That is why you will get the option D as incorrect. Okay, so now you know that option D is also showing the incorrect product, and you are left with option C as the correct answer. Okay, so this is the summary of whatever I have explained for the question, and you get that option C is correctly showing the main product formed in the reaction, which will be the Sadzef product. Okay, so I hope this question gave you a clear picture about the mechanisms followed in ether cleavages, and also how you get Sadzef product and Hoffman product in elimination reactions. Moving to the next question now, and again you are given an alcohol here, and you are asked which alkene is the main product of the following reaction. Okay, so we are treating this alcohol under acidic dehydration condition. Okay, we have added acid and heating the reaction, and we are expecting to get elimination of water molecule. But out of these four alkenes, which one will you get as the major product? Just now in the previous question we saw that when it comes to acidic dehydration of alcohols, we expect the Sadzef product, where the carbon-carbon double bond will be most substituted. So, let us discuss the mechanism once again. What happens? This hydroxyl group will be protonated, and you get oxonium here, where imagine the oxygen is attached to two hydrogens. Okay, so that oxonium ion will eliminate the water molecule in the subsequent step to give you a carbocation here. Okay, so now to get the alkene, you have two possibilities from where you can expect deprotonation, either from this way or this way. But the carbocation formed at the first step is actually a secondary carbocation. So this will get rearranged by hydrogen shift from this position. If one hydrogen from this position shifts to this carbocation, you get a carbocation at this position, which will be the most stable carbocation formed. Okay, so after the formation of this rearranged tertiary carbocation, now you have to deprotonate the carbocation to get a double bond. Okay, so you have two possibilities now. One is this side, one is this side. Okay, and these two sides will be similar, okay, because we have already shifted one hydrogen from here to get a carbocation here. So we will deprotonate from this particular carbon to get the Sage-F product here. Okay, anyway, this molecule is symmetric, so either from here or from here, after you got the saturated carbon here, after eliminating the oxonium, you eliminate the proton and you will get a double bond in this position or this position. Either way the product is same. Okay, so out of the four possibilities, this Sage product will be the correct answer. Okay, option A will be the correct answer. Here is the explanation. For acid catalyzed dehydration of alcohols, dehydration of tertiary and secondary alcohols generally occurs by E1 mechanism following protonation of hydroxy group, and the ratio selectivity follows Zizef rule. Thus, you will get this tri-substituted alkene as the final product. I hope this was clear. You had another possibility where you would have get a double bond here, like shown in the option C, but that will not be the Sage product. That will be maybe the Hoffman product, you can say, but in this mechanism you will not expect the Hoffman product. Okay, option A will be the correct answer for this question. After that, another question is here, which will be involving opening of epoxide. Which alcohol is the main product of base catalyzed reaction of epoxide in methanol? So we have already studied a lot of epoxide opening ring reactions already. So I hope this question will be now very easy for you. What happens? You are given methanol here, okay? So methoxide ion will be the one which will open up the epoxide ring. Okay. So you just have to identify the side and position from where the methoxide ion will attack. See, you are given this epoxide, okay? So you must know that the ring opening ring will follow SN2 substitution. So for that, the methoxide ion will attack at this epoxide ring from below the plane, isn't it? Because the epoxide ring is lying at the above the screen. Okay, so the methoxide must attack at it from below the screen. So we know the side of attack now. And then in the second step, we will identify the position of the attack. You have two positions, okay? One is disubstituted, okay? Disubstituted where one will be methyl substituent and one will be this alkyl, okay? And the other is monosubstituted. You just have this alkyl chain and one proton. So since there is no question of formation of carbocation, the methoxide ion will attack from the least sterically hindered position. So definitely this below side will be the preferred position. Okay. So now you know both the face of the attack and position of the attack. So what will happen? Simply the methoxyl will attack from this side, from below the screen of the laptop or phone, and the epoxide ring will get opened up, and O minus or OH will be pushed above the plane. So if you look at the options given, you can see that option D here will be the correct answer. Okay, because in option D, like we were talking, methoxide is attacking from the below the screen, and after the attack the O minus is getting generated above the screen. Thus, with this SN2 type mechanism, you are getting this particular alcohol as the major product. Okay, definitely this must be very easy for you now. Now, another question we have on the dehydration reaction: which cyclic alkene is the main product of acid catalyzed dehydration of cis 1,2 dimethyl cyclohexanol? This is cis 1,2 dimethyl cyclohexanol, and we are going to perform the acid catalyzed dehydration, which we have already studied in two of the previous questions. So, again, we just have to identify which product we will get. Either it will be Sedzef or Hoffman. Okay, one of these two options you will observe in the reactions. So you are given four different alkenes here. Let us analyze the mechanism that this reaction will follow. So what happens in acid catalyzed dehydration? First we get oxonium here because you have protons lying around in the reaction mechanism. Okay. So this hydroxy will take up a proton from the medium to give you the oxonium here. And in the subsequent step you will get water molecule elimination, and you get the carbocation formation here. Now this carbocation you have to neutralize by deprotonating the carbocation. And how are we going to deprotonate? You have three possibilities now. Okay, here you have the carbocation. So either you will deprotonate it from this carbon, or from this carbon, or from this carbon, which is this proton lying here. Okay, you have these three possibilities now. So if you eliminate this proton from here, you will get a double bond here. And if you eliminate a proton from this carbon, you will get a double bond in this position. And lastly, if you remove this proton, you will get a double bond in this position. So you have three options now. In the first case, you are getting a tri-substituted alkene. In the second possibility, you are getting a di-substituted alkene. And in the last possibility, where we are taking this proton for deprotonation, you are getting a tetra-substituted alkene. So you just have to decide now which product you want as the correct product. Definitely, it will be the one where we are getting the alkene which is the most substituted. And out of all these three possibilities that I explained, the tetra substituted one will be the major product. Okay, so option C will be the main product formed in this reaction. Again, the same explanation which you have already learned is given here. You may note down for your reference, and I hope you understood how we got this option C as the correct product. Okay, let us move to the next question. Now we are going to solve these questions from derivatives of carboxylic acids. Okay, You are given this, you can call a diester here, and we are hydrolyzing this diester with sodium hydroxide. So, in presence of aqueous sodium hydroxide, which of these four possible product sets will you get? Okay, you may already know that from hydrolysis of ester we get two products, one is alcohol and one is carboxylic acid. So in this particular example, in this diester hydrolysis, what which kind of alcohols and which kind of carboxylic acids you will get as the final product? If you look at the options given, option 1 is giving you two products where you have this alcohol, which is a diol, and this diacetate is given here. Okay, in option 2 you can see this diol is given and two molecules of carbon dioxide is getting generated according to option 2, and in option 3 you are getting a dialdehyde along with sodium bicarbonate, uh, sodium carbonate, and in option 4 you have been given this diacid and these sodium ethoxide. Okay, so which of these four will be possible? To know the correct answer, let us move to the mechanism that esters follow when it comes to basic hydrolysis. Okay, this is the mechanism of base catalyzed ester hydrolysis. What happens first? Hydroxide from the basic medium will attack at this electrophilic carbon, and you get the elimination of this good leaving group alkoxide. Okay, and after the elimination of alkoxide, first you get this carboxylic acid as the product. Okay, but the reaction doesn't stop at this stage. The alkoxide which is eliminated, this does not get proton from the reaction medium. Okay, why is it so? Because we are treating it with base catalyzed hydrolysis conditions. So the eliminated alkoxide will immediately take up the proton from the carboxylic acid formed, and in turn you get the alcohol after the formation, after the taking of proton taking up of proton by this alkoxide, you get this relatively stable carboxylate ion. Okay, so in the medium, until you do the workup, you have an alcohol and the other species in the reaction medium will be this carboxylate ion. Okay, I hope this was clear. So ultimately, as the product in case of base catalyzed ester hydrolysis, you get alcohol and carboxylate ion until you do the workup. So after workup, when you add water to the system, this carboxylate ion can easily get proton now, and you will get acid and alcohol which was earlier formed. Okay, so until you do the workup, always remember the stable carboxylate ion will be there in the medium along with the alcohol. So in this particular example, what were we given? We were given this diester and sodium hydroxide. So if it follows the similar mechanism, you can expect that the alcohol will formed after the hydrolysis, and you get the carboxylate ion at the other side of the ester. Thus, for this question, you will get a diol first, and the carboxylate ions will be there in the medium as sodium oxalate. Okay, because the carboxylate ions will get there with the counter cations sodium. So until you work up the reaction, in this particular question you will get ethane 1,2 diol and sodium oxalate. So among all these four options, option 1 will be the one which is correct. Okay, you will not get this acid, and the alcoholic fragment will not stay as the anionic form. Rather, you will get option 1 as the correct answer. Okay, I hope this was clear. And this is the general mechanism for the alkaline hydrolysis, which we have already discussed thoroughly. So after that, let us move to the next question. You are given an acid chloride here, and if we treat acid chloride in presence of palladium hydrogen, which is supported on barium sulfate, which product will you get? Is it an aldehyde, which is acetaldehyde, or will you get propanol, or will you get this acetone, or will you get this ethanoic acid? Which of these four options will be correct here? So what happens, the given reaction conditions is actually well known as Rosenmund reduction, which is a hydrogenation process where molecular hydrogen reacts with acetyl chloride in presence of catalytic uh, hydrogen on palladium, and this catalyst is supported on barium sulfate. So you can see here that this acid chloride is undergoing Rosenmund reduction conditions to give you acetaldehyde as the product. Okay, and in this particular reaction condition, when it comes to mechanism, you have to identify that the hydrogen is adsorbed on the palladium on barium sulfate surface, and this molecular hydrogen will be transferred to this carbon first, and carbon and chlorine bond undergoes cleavage, and the chlorine in turn gets adsorbed on the catalytic surface, and like that you get the Rosenmund reduction where you get the acetaldehyde as final product. Okay, so this chemical adsorption mechanism is being followed in this Rosenmund reduction, and out of these four possibilities you will get option 1 as the correct answer here. Okay, so after that, moving to the next question. This is a very easy question. Which of the following does not or do not give Cannizzaro reaction? You have four options, and this in this question, I must say more than one. Yes, yes. Okay. So in this question, I must say more than one options are correct. Okay, that means more than one substrates that are given in the question does not give Cannizzaro reaction. Okay, so so what happens for Cannizzaro reaction? Always remember you need alpha proton to be present. Okay, here is the summary. If you do not remember, you can go through these points. So, to get a feasible Cannizzaro reaction, you need an alpha proton, because in the course of the reaction medium, we need alpha proton abstractions. Okay, let us move to the mechanism to see what happens. You are given a basic condition in this. particular reaction, and mostly sodium hydroxide is used. Okay, so hydroxide from sodium hydroxide will undergo nucleophilic attack at this carbon center, and in turn you get this oxyanion, and another equivalent of hydroxide will take up a proton from this hydroxyl group to give you this kind of dianion. Okay, and this intermediate product which you get here will undergo attack at the second molecule of the carbonyl compound that is present. Okay, so uh, okay, I think by mistake I have said that compounds having alpha hydrogen will undergo Cannizzaro reaction. No, by mistake I have told you that what happens, compounds having alpha hydrogen will not give you Cannizzaro reaction. What happens when you have alpha hydrogen, you can expect aldol condensation in turn under similar reaction conditions. Okay, so after you get this oxyanion, this will attack at the second molecule of the aldehyde to give you the Cannizzaro reaction here. Okay, so this is the mechanism that is followed, and I'm sorry, by mistake I have said that to get a Cannizzaro reaction you need alpha hydrogen. No, compounds having alpha hydrogen does not give you Cannizzaro reaction. Okay, so I think in this question, if you ask that which of the following does not give Cannizzaro reaction, it will be the one of these four options which is containing the alpha proton. Okay, so the correct answer from these four options will be the option 4, because formaldehyde, benzaldehyde, and 2,2-dimethyl propionaldehyde, all these three are not containing an alpha proton. So these will give you Cannizzaro reaction. Okay, and option 4, which is containing an alpha proton, this in turn undergoes aldol condensation in presence of the similar reaction conditions. Okay, with that let us move to the next question. So this particular reaction is well known as Reformatsky reaction. Okay, and we will discuss how this Reformatsky reaction occur. Okay, so you are given an ester here which is containing this bromine substituent, and this ester we are treating it with zinc in the first step, and when zinc reacts with this bromoester, we will add benzaldehyde to the reaction medium. Okay, so this is a step by step reaction, and to know the final major product formed in the transformation, let us go step by step how this reaction is proceeding. Okay, so what happens when we add zinc to this bromoester? You get this zinc bromide intermediate, which is kind of similar to a Grignard reagent. Okay, what happens in that case? You get magnesium bromide as the counter cation, and in this particular case you get carbon zinc bond formation. And in the subsequent step, when we introduce benzaldehyde to the reaction medium, this the anionic part of this zinc bromide intermediate product will undergo nucleophilic attack at this carbonyl carbon. Okay, so after the attack, what happens? It will follow the similar pathway which we observed in Grignard reaction. Okay, so this carbon carbon bond formation takes place after the attack, and this electron shared electron pair is pushed towards the oxygen to give you oxygen ion, and you get a product similar to this. Okay, this is a carbon carbon bond that we have newly formed, and here you have O minus, which is partially neutralized by zinc bromide cation. Okay, but in the substrate you have another ester moiety which is highly reactive, and it is also in the vicinity of this oxyanion formed, isn't it? So the reaction will not stop at this stage, and we have not added any workup reagent or any water molecule till now to neutralize this oxyanion, so it will further attack at this ester carbonyl carbon, isn't it? So after the attack, you get this oxygen carbon bond formation between this oxygen and this carbon atom, and the electron pair is pushed towards the oxygen atom. Okay, so after the attack, in case of ester, you have this ethoxide good living group attached here. Okay, so immediately the oxyanion formed in the second step will eliminate this ethoxide to get you this newly formed carbon oxygen double bond in the product. I hope you understood the mechanism from this to this, and how we got ethoxide elimination to furnish this carbon oxygen double bond, which is a cyclic ester, which is lactone moiety you are getting as the final product. Okay, so first you got this carbon zinc bond formation which underwent nucleophilic attack at this center, and the oxyanion formed will immediately attack at the reactive ester moiety present in the substrate, and in turn the second oxyanion formed will eliminate the ethoxide to give you the carbon oxygen double bond. Okay, so thus you get this lactone moiety as the major product in the reaction, and if you look at the options given, you will get option 3 as the correct product. Okay, so this particular reaction is known as Reformatsky reaction, which involves a carbon zinc bond formation in the first step, and which subsequently undergoes nucleophilic attack at the electrophilic center. Okay, so with this we have arrived at this last question of today's tutorial. Let us quickly revise which questions we have today discussed. Okay, so in this fourth tutorial today we started with this Grignard reaction of ketone, which is a well-known procedure for the synthesis of alcohols, and we saw how the ethyl anion underwent nucleophilic attack to give you 2 methyl butane 2 all as the final product. Okay, and then we solved the this question where you had to identify A, B, and C, and we analyzed all the options to get option 3 as the correct answer. Okay, and we also looked at the easy mechanisms which are followed in this particular question, and then we moved to the very important epoxide opening reaction mechanisms, and we saw that epoxide ring opening reactions depend on the reaction conditions given. Okay, it follows two different distinct mechanisms in presence of acids and basic reagents. Thus, we also solved this question in the similar way. Since we did not have any acidic reagent in the medium, we got the attack from the least statically hindered side to get this alcohol as the major product. Then, in the next question, we had to identify the particular option which was showing the wrong main products. And after analyzing all the four options, we knew that option B was not showing the correct uh, option. Okay, so similarly, in the next question, we studied the mechanism of ether cleavage reactions in presence of acids, and also we studied the mechanisms of catalytic acid catalyzed dehydration reaction, and also this particular Hoffman elimination reaction. Okay, and we identified option option C as the correct answer, which was showing the correct product. Okay, and after this question, we saw this particular question we where we identified the correct product after treating this substrate under acidic dehydration conditions, and we saw the formation of most substituted SIDZEF product. Then again we saw this base catalyzed epoxide opening reaction, and the methoxide was undergoing attack from the below the screen, and we got option B as the correct answer. And then we came to this another reaction on acid catalyzed dehydration of cis 1 to dimethyl cyclohexanol, and we saw that when it came to di, tri, and tetra substituted alkenes formation, we preferably formed the tetra substituted alkene as the major product in case of acid catalyzed dehydration. Okay, and then in the next question, we studied base catalyzed hydrolysis of esters, and we saw that until workup, we get alcohol and carboxylate ion in the reaction medium. Thus, in this particular question, we saw the formation of ethane 1,2-diol and sodium oxalate as the product. And then in the next question, we saw that this acid chloride was undergoing Rosenmund reduction in presence of hydrogen palladium supported on barium sulfate, and we were getting acetaldehyde as the major product. Then in the next question, we saw which particular option of these four given does not give Cannizzaro reaction, and we saw that acetaldehyde is the one which contained alpha proton did not give you Cannizzaro reaction. Okay, and lastly we studied the mechanism of this Reformatsky reaction, which did not stop at the aldehyde stage. Rather, the oxyanion formed underwent uh, attack at the ester carbonyl to give you the lactone moiety as the major product. Okay, so with this we have arrived at the end of this discussion. I hope all these mechanisms you could understand correctly. So thank you all for joining. If you have any queries, you may ask. Okay.
Thank you, ma'am.
Okay, you're welcome. Thank you.